remember the idea of Ohm's law, because that is very important. We shall still use it here, that V is equal to IR. So this one is very paramount for you to know how it relates the potential difference, the current, and also the resistance. And also know something on connection of components. You're supposed to remember that when you connect components in series, the current is the same. And also when you connect them in parallel, then the potential difference across them is the same. So those are the things you're supposed to remember, so that as we check on resistor networks, you'll be able to go through it easily. So when we define resistors, now these are just devices that are meant to offer opposition to the flow of current in a circuit. So their work is just to offer resistance, so that if you have them if you have a circuit, you simply include them, and their work is specifically to offer that resistance. Of course, it's always required, and resistors have day-to-day application uses. I thought that they're always there in most of the devices. They're there in our radios and all those things. They're there, and they're important and required, of course. And that's why they have to be designed. And of course, they're always conductors. They have to be designed so that their work is just to offer that opposition to the flow of current. So there are different types of resistors, of course. We have variable resistors, and we also have fixed resistors. And of course, most of the times we shall be using the fixed resistors, which we normally call mostly carbon resistors. The symbol mostly is always this one. But of course, your book uses the symbol of this. So in most standard books or in future, just be aware that this is a symbol you'll be meeting most of the time for resistors, not the one you have in your syllabus. So mostly this is a standard symbol for resistor in a circuit. So nevertheless, I'll use the one that we are used to according to our syllabus, our curriculum, the one that we have there. So in our investigations, most of the times, and in our calculations, we'll be including this fixed resistor. Fixed resistor as opposed to offer specific amount of resistance. So they're designed such that in case, for instance, if it is designed to offer 20 ohms as its resistance, this is what it will offer. But when it comes to variable resistors, like maybe the rheostats, with them they can vary. They can have a range of maybe 0 to 50. So as you vary it, it can give you a range of 10, 20, 30, 40, depending on what the desired application. And they're also very important, of course, in the lab when investigating maybe how the current and voltage relates. You normally need something like a rheostat or a variable resistor that can allow you to vary the resistance, hence varying the current in it. So we'll take our study on fixed resistors and look at what we call resistor networks. That should be our main aim. Resistor network, just how we connect resistors in a circuit. And of course, the first one, we can have resistors to be in series. And connecting resistors in series, it's similar to connecting components or just bulbs in series. So it will suppose be a connection that looks like this. So if this is one of the resistors, you simply connect another one, just add to tail like that. So that is, there can be infinitely many based on your desired application. So if you have this kind of network, then these ones are said to be in series, and they can have different values. This one can be 4 ohms, this can be 10, this can even be 12, this can even be 2 ohms. So they can have different values. So those are the ones that are in series. And of course, you can complete, for simplicity, you can complete this our circuit and maybe give it a source of EMF or a source of voltage there of maybe 3 volts, like that. So when you connect them like that, we call that connection a series connection. So we may be interested to know what is the total resistance in this circuit, and also we may be interested to know what is the current passing through each of the resistors, and also we may be interested to know what is the amount of voltage drop across each resistor. So the first thing is to get to know what is the total, or maybe what you call effective or total resistance in this circuit. So in effective resistance, let's use our fundamental idea. We know that the voltage drop is not the same in each resistor, is different based on there. And also something that is common is current. We know that current is going to leave from this positive terminal, the conventional direction of current, like that, then gets to the first resistor, the second resistor, the third resistor, throughout, like that. So current will be the same current, that's the same current. If it is 2 amps, if it is 3 amps, that same voltage 0.26, that same current will be flowing through the whole resistors. As we had mentioned last time. So let's see if you had find we have said that the current is the same throughout. So let me just generalize for now. Call this R1, call this R2, and call this R3. Maybe this one can be R4. Like that. So to find the current, voltage through each resistor, you can use the Ohms law. So we know that current is the same. That is one thing we know. Current is the same current. So that I will be the same throughout. So then the voltage drop will be different. So if I want to find that voltage drop across each resistor, we'll be using the Ohms law, which says that V is equal to IR, like that. So through the first resistor, you just take the current times its resistance. Again, the next one, current times the resistance, like that throughout. So that you find the voltage across each other. Remember, the current is what is the same, while the resistance is for that particular resistor. So the voltage drop will be depending on the value of that resistor, and that is there, and all that. So we can proceed. So we can say that if they have the current, total current of I, that's the total current flowing with us in the circuit, and we also have the total resistance RT. We can call it RT or RE for R effective. So this one will be giving you the total voltage in the circuit. The total voltage is simply I times RT, the total resistance. The total resistance and the total current that is there. This is the total voltage that is there. We should be, in this case, it should be 3. So this one, we can equate it to the total voltage drop across each, because I said something that if you add the voltage drop here and here and here and here, they should add up the total supply voltage. So this same total supply voltage that I have here, IRT, can be given by finding the voltage drop across each resistor. And you have said that to just use the formula IR. So you just take at I times R1 for the first resistor. Then for the second resistor, we add again I times R2. Then plus for the third resistor, again the same current of I times R3. Then for the fourth resistor, again I times R4, like that. So what are these terms I'm writing? Let me repeat. This one here is the total voltage in the circuit obtained by just getting the total current and the total resistance or effective resistance. And this is a total voltage, which should be the same as the individual voltage drops in each resistor. So this for voltage drop in first resistor, the second, the third, and the fourth. Then on the right-hand side, we can factor out I, because I is common throughout. So this will be the same as I R total or R effective will be equal to factor out I because it is common, so that you have R1 plus R2 plus R3 plus R4, like that. Then, of course, with the mathematics, you can, because I is common, both sides, you can cancel this I and this I, and then you'll remain with RT will be equal to R1 plus R2 plus R3 plus R4. Now, what is important? What does it tell us? That if you have resistors connected in series, then the total resistance or the effective or equivalent resistance is obtained by adding the individual resistors of all the resistors in that circuit, just the sum. So if the resistors are 4, just add their resistance. If there are 10, you add them like that. So this one here can go up to plus. You can continue up to Rn based on the number of resistors you have. You just add them. So if there are 2, just R1 plus R2. If there are 3, R1 plus R2 plus R3. If there are 5, R1 plus R2 plus R3 plus R4 plus R5. That's how you obtain the total resistance in a series connection of resistors. So we have used something fundamental, that the current is the same, of course. And of course, another thing is that the total resistance is this what you obtain it from. You just add those resistors. So for instance, in this example that we already had, the example that is already here, I had given the values of the resistors here. So you can even find the total resistance, that's the case. So the RT or R effective will be R1, there are 4 of them, R1 plus R2 plus R3 plus R4. Then just bring in those values. So we have them as 4, 10, 12, and 2. 4 plus 10 plus 12 plus 2. And then this will give you
28.
28, thank you, 28 ohms, like that. So that is how you find the total resistance. So the first thing in any circuit that involves resistors is always to find the effective resistance, or you can call it the total resistance or the equivalent resistance in the circuit. And that's how you obtain it. So if you have components in series, you want to find the total resistance or the effective resistance in the circuit, then you simply add them. So, and that is how you're supposed to get it. Any question on that part? Up to where you have stopped, any question? Right, then you can proceed. So we may also be interested to know what is the total current that is in this circuit. So another question can be asking you to find the total current flowing in the circuit. So this same current, you are saying that, oh, the current is the same, what is its value? So let's maybe try and find the current, the total current that is there. The total current, again, you'll come and use the Ohms law. So from Ohms law, we say that V is equal to IR. The total current I should be the total voltage that is being supplied divided by the R effective or the R total that is there. So the voltage, it was connected to we had 3 volts that is coming in there. So we have 3 divided by the R total or R effective, which is 28, divided by 28. And that will give you the total current that is flowing in that circuit. So into 4 significant figures,
0.1071.
1071 amps, like that.
Yes.
So that is good. That is the current that is flowing in this circuit. That is total current that is flowing in this circuit. And we have said that the current is the same. So that current of 0.1071 is the current that is this one here, I'm showing the arrow, the same current that comes in, the same current that gets into R1, that is 4 ohm resistor, the same current that will pass through the 10 ohm, the same current that passes through the 12 ohm, and also the 2 ohm. So somebody can ask you now, if somebody asks you to find the current through the 10 ohm resistor, for instance, maybe somebody asks you to find the current through the 10 ohm resistor. So if this question comes and this one is not there, this one of total current, then suppose you do the same thing, because the 10 ohm is simply the current that. So maybe a task can only come in when I may be asked to find the voltage drop across the 10 ohm resistor, the voltage drop. So for the voltage drop, you need to calculate, use the current that is passing through that resistor and also its resistance. So again, you'll be using the Ohm's law. V is equal to IR. So you check what is the current passing through that particular resistor. We have said is the same current, 0.1071 times the resistance of that resistor you are dealing with, which is 10 in this case. So when you multiply, you'll find 1.071 volts, like that. So when doing this question, also be on the lookout. If you are getting your value of it to be maybe 20, and yet the total voltage supplied is 3, you should know that there's a problem somewhere. So also try to check if your answer makes sense. Like for instance, the total voltage given in the circuit is 10, and your answer you're having 30. It's not possible. So that is how you will solve that problem. If asked to find the voltage drop across any resistor, just check the current flowing through that resistor times its resistance, the portion it is offering to the flow of current. Any question? Any question? So I will have to go to this parallel connection. Are you okay with that series one?
Yes.
Yes.
Yeah, so but you have to understand the individual one. You have to understand the series first, then understand the parallel one. Then after that, now we can do the combined one, because the combined is one that will be tested. That will be tested most of the times. It will be combined, but we require to know the knowledge of how we deal with it when it is in series, and also how to deal with parallel ones. So let me go to parallel connection, maybe a parallel one. So for parallel, we connect them, I can say maybe side by side or something like that. So you'll have them, if that is the first one, and then you have another one. So that I don't draw a very big diagram, let me maybe use 3. These 3 will be connected. Then you connect them maybe to a source of voltage. So maybe 10 volts supply is there. So these R1, I can give them their values as well. So the first one, let me give it 6 ohms. This one I can give 4 ohms. Then maybe this one I give 10 ohms. So we have R1. This one will be R1. This R2. and this R3. They are connected in parallel, so that all their heads, maybe if you can say that, are going together, then the tails together, then they all get to the source of the EMF, such that they are under the same potential. So we say that this end and this end, anything within this region have the same potential. And therefore, for parallel connection, the one that looks like that I've drawn, normally the voltage drop, of course, will always be the same. So this 10 volts is what will be measured in the 10 ohm resistor, in the 4 ohm resistor, and also in the 6 ohm resistor. But so let me say that we have that same voltage drop. We'll pass through them, that of 10 volts, maybe will pass through them. Then now when it comes to current, we say that the issue of the junction, the Kirchhoff's law will come in now. The current will come like that. Then if we reach this point, it will meet a junction. So some current will go through that path, others this path, and others this other path, like that. So those three paths will be followed. And of course, the path that will get the greatest current, the path that offers the lowest resistance will get the greatest current. So we may be interested, of course, when given this kind of a circuit, we may be interested to know, now that I have 3 resistors connected in parallel, what is the total or effective resistance in this circuit? And at the resistance in the circuit. So the total resistance in the circuit, R total, will begin again by just the total voltage divided by the total current. Total current in the circuit, of course, like that. So this one also allows us to talk of the similar. You can say that whatever is the total current in this circuit as well, you can give it in terms of any expression. You can give it in terms of that way, or you can say that the total current in this circuit should be the total voltage divided by the total resistance. That one is also allowed. Or you can also say that the total voltage in this case is simply given by the total current times the total resistance in the circuit. So we know that current is different, of course, in each case, but the voltage drop is the same. So let's use this expression, the one I've written, the implied one here, which the total current in the circuit should be the total voltage divided by the R effective or R total. So let me use the word effective now. This is a total current. Total current is V over RE. But we said something. When you have components in parallel, the total, yes, the current differs, but if you add all the current passing to the 6 ohm, 4 ohm, 10 ohm, they should add up to the total current that is in this circuit, this current here. So it should add up. So the current, if the current is maybe 2, if it is 2 amps, then in the 6 ohm, 4 ohm, and 10 ohm, you add all that should give you 2 amps. So in this case, we can now try to find expressions for each particular current. Let's find expression for the current passing through the 6 ohm, the 4 ohm, and also the 10 ohm in terms of R1, R2, and R3. So using the Ohms law again, we know that V is equal to IR. So current just V over R. The voltage is the same. So voltage of V over R1 for the first resistor, then plus the voltage is the same, V over R2 for the second resistor, then plus V over R3 for the third resistor. Then we do the same thing on the right-hand side. V is common in the numerator, so you can factor it out. V into, so this side you'll have 1 over R1 plus 1 over R2 plus 1 over R3. like that. So even on the left, if you like, you can find out V. So it will look like this. It look like V times 1 over RE. So that allows you to cancel V from both sides, what is common, so that you have the remaining expression to be 1 over RE equal to 1 over R1 plus 1 over R2 plus 1 over R3. And now this is the expression that will give you the total resistance or the effective resistance in the circuit. So this expression tells you that when you have components in parallel connection in a circuit, or to be particular, if you have resistors in parallel, then the reciprocal of the effective resistance, this one here, the reciprocal. So don't confuse and talk of R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. We talk of the reciprocal. So the reciprocal of the effective resistance is equal to the sum of the reciprocals of the individual resistance. So that's what we have there. So regardless of the number, this one you can just add all the way up to infinity, 1 over maybe R n. Regardless of how many they are, even if towards positive infinity, it doesn't matter. So that is the how to find that that effective resistance. Then we have a special case. So a special case can come in. Now a special case is where we have two resistors in parallel. Let's derive something from here. For two resistors, we have that 1 over R total or R effective. We have said that it's supposed to be the reciprocals. So it will be 1 over R1 plus 1 over R2 because there are only two resistors. Then in this case, let's focus on the right-hand side and solve it as a fraction. So this will be 1 over RT will be equal to. Now here, we check the LCM of R1 and R2. R1 times R2 is just R1, R2. Then we check R1 goes into R1, R2 how many times? Should be R2 times. So R2 plus R2 goes into R1 and R2 how many times? R1 times. Times 1 is just R1. R1. And you're allowed to rearrange that. R2 plus R1 is the same as R1 plus R2. So can be R1 plus R2 divided by R1, R2, like that. So from here, you can take reciprocals, both sides, in both sides of the equation. So 1 over RT, the reciprocal will be RT, will be equal to, take the reciprocal also this side. So will be R1, R2 over R1 plus R2. Again, this is something that is important for us to remember, in that if you have two resistors in parallel, then the total resistance can be given by the product over sum. So this is more of the rule of product over sum rule. Product over sum. Product divided by sum rule. So it is the product of the resistors divided by the sum of the resistors. Only applies for the special case when the resistors are two and are in parallel. So any question? Okay. If there's no question, we can proceed now, solve this specific case that we have here. This case that we had here. So we had the voltage being 10 volts. We had the resistors being 6 ohm, 4 ohm, and 10 ohm, and all that we have. So the first question will always be asked, find the total or effective or equivalent resistance in that circuit. That will be always the first question. So that first question, let's solve it here. So the effective resistance, effective or total? Total resistance. There are three of them. So our formula says that 1 over R effective should be given as 1 over R1 plus 1 over R2 plus 1 over R3. Then you come and say that 1 over RE, where R is effective, will be given as 1 over, what was the value of R1?
6.
6, okay. Plus R2?
4.
4, thank you. Then R3?
10.
10, like that. Then please solve this algebraically, like the way you do solve in mathematics. There's nothing big deal here, just the same as 1 over RE is equal to, just add 1 over 6 plus 1 over 4 plus 1 over 10. You can even add using a calculator.
31 over 60.
31 over 6.
60.
Someone confirm if that is true.
31 over 60.
Okay, good. 31 over 60, like that. So that is 1 over RE. So we need to find RE. Now to get RE, now the effective resistance, you take the reciprocal both sides. So take the reciprocal of 1 over RE will give you RE. Then reciprocal of 31 over 60 is simply 60 over 31. Then you can simplify that now and give me as a decimal. We don't give fraction answers here, so except in specific cases.
1.935.
935.
5.
All right. Now look at that, ohms. Look at this. You learn something that is interesting, that if you have resistors in parallel, then the effective resistance will always be smaller than any of the smallest resistors that in that circuit. For instance, our circuit had 6, 4, and 10. Look at the effective resistance, 1.935. Will always be small. And this one will explain to you something, why when you have bulbs connected in parallel, they tend to be brighter than bulbs connected in series, because those bulbs are treated as resistors, as loads. So if you look at their resistance, they add up to give a very much lower resistance if they're in parallel, and therefore less opposition to the flow of current, and the bulbs will be much brighter. If you have bulbs connected in series, then the resistance is added and therefore increases to be a very much bigger value. Therefore, the bulbs will tend to be dimmer or less bright. So that's something to check on. So again, if dealing with the parallel circuits, parallel resistors network, and you have seen the values there, 6, 4, 10. Alafu wewe unakuja unapata total resistance to be 20. It's not possible if they're in parallel connection, or even 30. Most of the cases, all of the cases, it always add up to be something much smaller than even the individual resistors that are there, if they're purely in parallel. So that is the total resistance that is there, or equivalent resistance. And if you had to find, maybe there's a question somewhere.
Yeah, pardon the last part.
The last part of the solution, or what I was saying.
Yes, what you were saying.
About bulbs.
Yes.
Or about how to evaluate your answer.
Yes, how you can confirm that your answer is right.
Oh, okay. So you check, for instance, in this case, we know that when we connect, okay, from the solution we have just had here, check, we had resistors. The value of those resistors in parallel were 6, 4, and 10. When you have computed our answer, we have found the answer to be 1.935, which is smaller than any of the individual resistors. And this will always be true for any kind of connection that is purely parallel. So it means that if you are doing this problem and you find your answer to be something like maybe 8, something like 10, something like 20, then just know that automatically this one is not correct if they're in parallel connection, because you expect the answer to be lower than 4, the lowest, and cannot be greater. So if you are doing this connection, you get your answer to be finally maybe to say 19.35, you should just say that there's a problem somewhere and recheck your work. That's what I was saying in evaluation of your answer. So normally, as you solve, this rule applies in mathematics and even in physics, both of the mathematical subjects. There's an answer that if you get, you should just be worried. Can this really be an answer? If you are solving, always after solving, you get your answer. Try to see if that answer makes sense and can fit in the problem. You somehow evaluate it and look at it and see if it makes sense to you. It will also be a quick way to know whether you have done a mistake in your, because you can, it's a normal, we are human beings, you can do a mistake as you do the calculation. It's possible. Maybe it was 31 over 60. If we do in the calculator, you placed 31 over 6 or 6 over 31. It is normal. So by checking your answer, if it makes sense, can always help you to identify the mistake that you did. Okay, I hope that is done. So that was the first question. I'd asked you to find the total resistance or the effective resistance in the circuit. So the next one, I want you to find the voltage drop across the 4 ohm resistor. So who can give us that answer? What is the voltage drop across the 4 ohm resistor? I hope you copied the question. What is the voltage drop across the 4 ohm resistor? What didn't have 4 ohm resistor here? Yeah, it was there. Here is the question we're dealing with. This circuit here. Someone can try. What is the voltage drop across the 4 ohm resistor?
10 volts.
10 volts. Very good. 10 volts because we say that these components that are all in parallel connection. And therefore, for the sake of parallel connection, the voltage drop should be the same because they're under the same potential. So this same 10 volts here will be the voltage drop across the 6 ohm, 4 ohm, and 10 ohm when the devices are in parallel connection. The voltage is the same that flows through them. The voltage drop, the potential is the same. The potential difference is the same. So this is simply 10 volts. So what about the current? Of course, now current in the 4 ohm resistor, that is passing through the 4 ohm resistor. So in that case, for the current, you have to calculate because you say that the currents will be different. So you come and say that from your Ohm's law, V is equal to IR. The current I should be given as the voltage drop across that resistor divided by the value of the resistance of that resistor. So this will be I will be given as V, which is 10, divided by the current, which is divided by the resistance, V is 4. This will give you 2.5 amps, like that. So that is the current that is flowing through the 4 ohm resistor. Now let's check something. Let's check let's check and try to calculate the total current in this circuit. What do you expect? Do you expect it to be higher than 2.5 or less than 2.5? The total current in the circuit.
High.
Higher.
Yeah, we expect it to be higher. So let's just maybe calculate it as well. The total current the total current we have in the circuit. Total current will be given as I is equal to V over R. So V is the total voltage, and then you divide by the total of the effective resistance, which we found to be
1.935.
Where did we calculate it?
There.
This one?
No.
Is it this one?
No.
Mtu anasema no. But I think that one, 1.35. That was
1.935.
1.935.
Oh, it was 1.9.
Yes.
Oh,
You
must
have updated.
thank you for that. 1.935. 1.935. So let's just calculate. We see what we'll get. 1.935. So 10 divided by 1.935. I'm finding 5.168.
168.
Yes.
So that's what I'm getting. At least it makes sense. V, I'm A. Yes, that's the total current in the circuit, and you can see that the current through this one is 2.5. So if you like, and you have the time, try calculating the current through each of these. Try to find the current through, where is it? Through the 6 ohm as well, then the 10 ohm. Then you can add and see if it gives you the total one that you have just found there. Somebody want to try that? Through the form, the one that is through the form, we had already found that. So maybe the one to the 6 ohm. So the one to the 6, you can say that's the 6, not the 6, but I is V over R. So it is the 10 divided by the 6. So 1.66, 1.667. Then the other one is the one through the 10. So the 10 divided by the same 10, you'll find 1.0. Then you try adding all of them. So this is 2.667. Then we add to the one we found that was for the 4 ohm, was 2.5. So is it giving almost the same answer?
5.167.
Yes, something around there. It gives 5.167, which is, if you check, almost the same as this one. So the issue of rounding off also comes in, because here we rounded off something here. So if you didn't round off this one, it will have given you perfectly the same answer. So I think that is a parallel connection. We can stop there so that we do look at now the combined one, or a series parallel connection now.
Excuse me, sir, I have a question.
Yes.
Is there any penalty if you use the 60 over 31 to divide the 10? Is there any penalty for dividing 10 by the fraction?
There's no penalty. Actually, it is good because it makes sure that you are accurate. It is allowed. It's good. Actually, it preserves the accuracy of the value. The only problem is that in physics, we encourage most of the times our answers, the final answer should always be in decimal, unless in a few cases where we allow fractions. And those few cases where we allow fraction, one of them is in refractive indices. Like for instance, the refractive index, if it is 2 over 3, not 2 over 3 will turn out to be, in decimal form, will be 0.666, then we'll have to round off to 7. which will be less accurate compared if it was to be 2/3. So in that cases, we can allow fraction. But most of the other computations, we encourage that the answer will be in decimal. So in the process of calculation, if you bring in a fraction to help you be accurate, there is no penalty. Any other question? Any other question? No question, so we are good, we proceed. Okay, I think that is enough for us to begin with. So so let us do a combined connection, or maybe a combined connection of series and parallel connection. So this is whereby we have some resistors being in series, some being in parallel. And I'll just go straight away to an example, then we see how we can solve it out. And I'll begin the simplest combination, something like this. Like that. So I can give the values to be, let me have this 4, the first one 4, this 2, and this 1. Like that. So we may be interested to combine this resistance. Of course, when given this combined, this combined connection whereby you have some resistors in parallel and others are in series to the rest, the first thing will always to be able to get the effective of the total resistance. Okay, where did I lost you at? Hello, you're able to hear me still, right?
The sound.
Yes. Yes.
Yes.
Okay, so let me get back. to so I hope we are able to. Yes, so that is what I was saying. We have that kind of network, and we are supposed to find the effective resistance. That was the first question. So I'm saying that you begin the one that is in parallel connection, this one here, so that you reduce it. So you combine the two, the 1 and the 2 ohm resistor, combining. So the first one combining 1 and the 2 ohm resistor. The two of them are in parallel connection. So you're going to see that the R total for them will be, and only 2, so you can use the product over sum rule. So R1, R2 over R1 plus R2. So this will be 2 times 1 divided by 2 plus 1. What do you get?
2 over 3.
So you get 2 over 3, every 0.06667 ohms. That is combining these two. So if you are to redraw, you can redraw that circuit by making it look like this. You have on the left, you have the 4 ohm resistor. And then you can have a single resistor now to represent the two that are in parallel. The one that is 0.6667, like that. Then now the two, if you check this and that, they're now in series. So you can find the R total by now adding them. So that will be the R effective. You now add this 4 plus 0.6667. And then that will give us 4.6667 ohms, like that. So that will be the same as talk about one single resistor that has a value of 4.6667 ohms that can replace the whole system. So instead of having a connection that has this kind of connection of 3 resistors, some in parallel and 1 in series, you can simply have 1 resistor of 4.6617 to replace that whole system. So that is how you find the effective resistance. Now this redrawing is not part of what you mark. That one you can do somewhere else, maybe with a pencil up or candle. Our work is just to mark for you the working. We're only interested in what you are working only. Those structures of redrawing, you can have them somewhere with a pencil candle, just for your own personal work. So any question on that are effective?
No.
Mwalimu, we can't hear you. We can't hear you.
We can hear you perfectly.
So I don't know whether everyone was not able to hear me or only some few.
Everybody.
You had muted your mic.
Oh, that was a mistake. But now what about this one who is saying that he was able to hear me? You need PR, ama-
You're still talking now.
Wow. So all the solution I've done myself.
Yeah.
I was
Yeah.
talking to myself in all that
Owino.
solution.
Yes.
Right from the beginning of total resistance.
No.
So you can tell me from which part so that from the total current?
Yeah.
Yes.
Yes, Apple.
Okay. Okay, thank you. So I was saying that for us to find the total current, we have to find the total voltage divided by the total resistance in the circuit. And the total voltage, I'd said that I gave a supply voltage of 8 volts to be in the circuit. So it will be that 8 volts you divide by the total, R total, which we had just calculated here. This one here, the value we have up here, 4.6667. And that's what we are dividing as 8 divided by 4.667. And I was requesting for an answer, only to be told I'm muted. So that would be
1.7143.
143. So that is the total current that is there. And that current, based on from the previous work, that current, which is total current, should be the same for any series connection. So what does it mean to us? It means that that current of 1.7143 is the current that is flowing through this 4 ohm resistor, and the same current that is flowing through this combined resistor. So this system, this one here of 2 ohm and 1 ohm, they have a total current of 1.7143. But that current is not the same for all of them, because that in parallel connection, that current needs to be different. So what we can find for them, we can find the voltage that is similar to them, that is common to them, the voltage drop. So that's what you use. Use this current that is common to them. Their total current will be this one for the 2 ohm and the 1 ohm, the total current. Yes? I'm muted again.
No. We can hear you.
Okay. So this current here, because it is common to a series connection, it is the same that passes through the 4 ohm and also this reduced 2 ohm and 1 ohm resistor. So that is a common current that is through them. But we don't know whatever is passing through this and whatever is passing through this. So you can find the potential difference, because you know that the potential difference should be the same for all of them. So you come and say that if you want to find the PD, let's say maybe the potential difference across the 2 ohm resistor, you can have that as a question. Maybe the potential voltage across the 2 ohm resistor, this one here. Use the formula V is equal to IR. So the current would be the current that is flowing through the total reducer there, which is 1.7143. So 1.7143 times, now the R here, use the effective. Remember, this current is flowing through the reduced one, through this one, not through the individual ones, through the reduced one. So you use this effective resistance here of 0.667. 0.6667. That is how you get the voltage drop across, that is across them. So if you can compute that, you will get one. Is it one? Does it make sense? Can it be
1.143.
1.143. Does it make sense? Does it make sense for us? Okay, what was the total? Did you get total current anywhere? We can check. Try and check. Total current was 1.17, 1.7143. Now multiply by the resistor here. Resistor here is 4 for this one here, times 4. And see if you what the value you get, if you add to this, should give you around 8. The value you get, if you add to the one you are getting right now of 1.143, should give you 8. Just check if it gives you something around 8, then we are correct.
Yes.
It gives, right?
Yeah.
Very good. Then we are correct. So this is a voltage drop that is across the 2 ohm resistor. And that voltage drop of 1.143 is the one that is through the 2 ohm and also the 1 ohm. So you can find even the current through the 1 ohm or even the current through the 2 ohm. So if somebody now asks maybe to find the current through that 2 ohm or even the current through the 1 ohm resistor, current, let's find the current through the 1 ohm resistor now. So the current, again, just using the formula from V is equal to IR, I should be equal to V over R. The voltage drop, the one you have calculated above, 1.143. Divide by its resistance, that is 1, and the answer will be 1.143 amps, which again needs to be, let's check the total current that was in the circuit, was 1.7143, and this is 1.143. So it makes sense. It has to be less or equal. It can't be more than. So the secret is just to use what we have been saying, how to know the effective resistance, and also you need to check when you have them in series, what is common, what is different. If you have them in parallel, what is the same for all of them and what is different for all of them? That's what you need always to remember. Any question before I give now maybe an improved one? Are you okay?
Yes.
Now I want us to just try and introduce for me this network I want to draw here. Let me get more space. So that's the first thing. Once you get that effective resistance, then it gives you a way of start now working backwards with that to get the values of current and voltage across each and every resistor. The first important thing is always to be able to reduce that resistor into maybe one or maybe what you call equivalent resistance. So I want to give one. You attempt, just try get for me the effective resistance, and then from there I will give you the other questions. Then we can maybe solve them also together. So you have this here. So this one here is 8 ohms. Then this one comes like that. This one is 6 ohms. Then this comes. This one, 4 ohms. Then we bring another one down here, 2 ohms. Then this completes. So the current gets in at that point, then it comes out at that point. So the first question, of course, let me give you what? Yes, I can give you the value of the current that is coming in so that this question looks a little bit different. I give you the current. So the current coming in at this point is 4 amps. Yeah, that's the current that is coming in, 4 amps. And that's the same current that goes out again. I can also give you here that I that is coming out is also 4 amps. So the first question is to find, for me, the first question, find the, or determine the total resistance or the effective resistance in the circuit. Total resistance. Then part B, the voltage drop across the 8 ohm resistor. Voltage drop across the 8 ohm resistor. Then part C, the current through the 4 ohm. Current through the 4 ohm resistor. So you can try that, then we solve it together. So all of us, we are trying it. Usikae tu, umetulia. So you should be through at least with the first part.
We can't see the other questions.
So I need to get your values, your answers. So let me clean more space for solving it. It should be true. So I'm not able to read the charts. So if you, once you're done, you can just unmute and tell us your answers. Or there are some of you have already posted the answers in the charts. We can go and check maybe. So I'm having 1. Now what is this? 142. So no one has posted the answer here. So we can question 1. Someone is giving me 4.2. 4.2 for part A, and then someone is giving me question 1, 3.2. Somebody is giving me 20. What is this now? 21/5. Abdul Malik Yusuf, we have been singing all along that you can't give us our answers in fractions. We are still giving 21/5. So it should give us a decimal, not as a fraction. So I'm seeing 4. Question 1, 4.167 ohms, 4.167. Okay. Now, let me solve it. I see what it turns out to be. Most of you are getting 4.167. Yeah, 4.2. Brown 4.168. Warren 4.2. Mwenda Kirimi 4. Finley 4.1. Tunay Bren 4.1. Ryan 4. Okay, good. Now let me come, because of time, let's solve it together. We see you can cross-check with your work. So the circuit is there. That is it. So we are having 8 ohms there. Hey, what happened to it? I erased. Yes, it was like that. So we are having 8 ohm there, 2 ohm, 6 ohm, 4 ohm. Right. So let's see and redraw. So the first thing I want us to redraw this circuit so that it looks better. So that circuit is given as this way. Let me make it smaller so that I'm able to draw up kando yake the reduced one. So it was like that with the values 8, 6, 8, 6, 4, 2. So we have 8, 6, 4, and 2. Then coming in at that point, then coming out at this point. So this is how you're supposed to redraw that circuit. You begin with where the current is coming in. So from the left, confirm that you're able to hear me.
Yes, we can.
Yes, we can hear.
For you to solve this problem, you have to redraw it correctly.
Yes.
Correct. So this is how you begin. You check from where the current is coming in. If the circuit is complete, that you have a positive terminal, you begin from the positive terminal, then you follow through the current. So our current is from this point here. So you bring in that current, then the current will come and meet a junction. The junction goes to 8 and also to 2. So you create your junction this way. And in this junction, you give it up here, it will be going through the 8 ohm, while down here it will be going through the 2 ohm resistor, like that. Then now you can decide and follow one path. For instance, you follow the first path from 8 ohm, it proceeds and continues to the 6 ohm. So you're supposed to continue with it like that until you reach the 6 ohm resistor. So this will be the 6 ohm resistor. Then from the 6 ohm resistor, it is coming and joining with the one from 4 ohm resistor. Now, if you check the 4 ohm resistor, it is from the 2 ohm resistor. So the current will come, pass through the 2 ohm resistor, then come through the 4 ohm resistor. So you come and draw the 4 ohm resistor there, like that. Then you can check here where the junction is coming in. It is from the 4 and from the 6. So the 2 come and joins like that as it goes out. So the current came in through this point and goes out through that point. So you have to redraw it correctly like that. That is just you redraw so that it looks much better and easier to interpret. So from there, you can easily find out the total effective in each case. For instance, you check at the top part here. These two are in series connection. So you can add them together. So if you add 8 plus 6, you get 14. So at the top there, you can again redraw this way. So we have that. The branch is there. So top here, we can have one resistor to replace them. And that will be 8 plus 6, which is 14 ohms, like that. Then again, the same thing at the bottom here. These ones are also in series. So you can have one resistor to replace them. You add because they're in series. So you come and add them. And 2 plus 4, you get 6, like that. So that's the second one that we have just reduced, like Evo. Then now the third one, now the final one, we can reduce by taking, of course, in your working, you don't expect it to draw for us. They're supposed to write the solution. You say that the RT for the first one, 8 plus 6, to get the value. Then this other one, 2 plus 4, you get the 6. So the final one, the 214 and the 6 ohm are in parallel connection. So for that parallel connection, we are going to have that R effective or R total. The question was about R total. So R total will be R1, R2 over R1 plus R2. It is a product over sum, the two. So it will be 14 times 6 divided by 14 plus 6. And this will give you 14 times 6. Yes?
We need 14 times 6 is 84.
Okay, divided by 20.
4.2.
4.2.
4.2 ohms. So you can check your work. So this one can be replaced by one resistor. Check on my left-hand side here. That has a 4.2 ohm. The whole system there can be replaced by a 4.2 ohm resistor. So you can check. If you got it, you can give yourself the 3 marks or the 2 marks, the 3 marks. If you did not get it, you have, at least you can now see where you went wrong. And of course, it was on the redrawing how the resistor should look like, the network. So that is 4.2. So once you get this one right, then other questions you can get them right as well. If this is already wrong, then just know that everything that will follow is always unfair, but anything that will follow after that will always be wrong once the total resistance is not correct. So if you got 4.2, that's the correct one we need to proceed with. So that was the first question, find the total resistance in the circuit, and we have done that. So the next one is the voltage drop across the 8 ohm resistor. So check in your diagram, the 8 ohm resistor, that's where it is. It is here, this one here. So we need to find something. For us to get into the circuit and start working in that network, we need to first of all know what is the total current in this system and what is the total voltage in this system. One thing we are given, the total current we're given here to be 4 amps. So we can also find the total voltage that is flowing here. Now, why do I need that? Is because check how I've reduced my resistor. I have this one here. Then for this case, these are in parallel. These ones are in parallel. And for this parallel, one thing that I know is the same through them is the voltage drop. So and that's why I need to find the total voltage that will be the same through them. So the first solution for solving that part B would be finding the total voltage. So part B is find the total voltage. So voltage is given as IR, and I will be the current that was given in the circuit, which was given to be 4 times the total resistance. So this will be R total resistance that you have gotten up here to be 4.2. 4.2. So this will give you 16.8. Eh?
Yes.
Yeah.
16.8 volts. Now that is the total voltage in this circuit. The total voltage is 16.8. So this 16.8 is the one that will pass through. Let me have a black pen here. Now that 16.8, the one that is passing through here, 16.8, or might be the potential drop that is there, and also the same potential drop that we have here, 16.8. They're the same because they are in parallel. They are under the same potential. So this 16.8, we can move backwards and even find the current that is here now. We don't have the current in the circuit, so we can find the current that is flowing through that. We already have the voltage and you have the resistance is 14. So let's find the current that is flowing there. So that current will be given by, from V is equal to IR, I is equal to V over R. The voltage, which is 16.8, divided by the resistance that we have up there, which is 14. So divide that by 14.
1.2.
1.2.
1.2 amps. Thank you. So 1.2 amps. So that 1.2 amps is the current that is flowing through this 14 ohm resistor. And this 14 ohm resistor, don't forget, it was in simpler combination of 8 and 6. And the 8 and 6 were in series. And for series, we have the same current flowing through. So that current of 1.2 we have gotten is the current that is flowing through 8 ohms, so 1.2 amps, and also you have 1.2 amps there. The same current is flowing through the two of them. So from there, you have the current, you have the resistance. You can find now the voltage drop across that 8 ohm resistor. So the voltage drop V will be IR, and I is that kind of 1.2 times the resistance of that particular resistor, which is 8 times 8, and this will give you 9.6 volts. Anybody got that 9.6 volts?
Yes.
Yes.
Who is that? We can clap for you. Who is that? You clap for yourself. But that was good. If you managed to get 9.6 volts, that was good. This question will have been divided into sections, but I gave it all together just to see how you work on it. Something you should always notice is that these answers will always flow. What to get your answer in part A will always be used in part B, and it will always be continuous like that. Like we got 4.2, it requires to be used somewhere here. Once you get this answer of 16.8, it requires to be used somewhere here. Once you get your 1.2, it's required to be used down here. So it always progresses like that. The question in part A the question in part B may require something in part A, and the question in part C may require something in part B. So always try to be very accurate as you do your steps moving forward. Then maybe part C, the question is find the current through the 4 ohm resistor. So let's get back, just get back to your decomposed, reduced resistance, and you see resistors. You see, we want to find the current through the 4 ohm. 4 ohm. So identify where 4 ohm is. Which pen color now? Blue. Okay. No, blue we have used. We can use green. I don't know that it's visible. So we want this one here, the 4 ohm. So check 4 ohm was down here and it was reduced to 6 ohm. And there's something we have about the 6 ohm resistor. We know that the voltage is 16.8. We already found that in the previous section, 16.8. So you can also find the current through this system, all of it. So the current there, current I will be V over R, which is the voltage is 16.8. We found that up there, divided by the effective resistance where that 4 ohm resistor belongs. It is 6. And when you divide that, you'll get
2.8.
Yeah?
2.8.
2.8.
2.8 good. 2.8 amps. Now this 2.8 is a current that is flowing through, let's go back to a diagram, through the 6 ohm resistor. And this 6 ohm resistor was a combination of 2 and 4. And they were in series. And for series, you know that the same current flows. So the same current of 2.8 is the one that is flowing through the 2 ohm resistor and also flowing through the 4 ohm resistor, 2.8 amps. So our answer is just that, just 2.8 amps. That is the same current that flows through the 4 ohm resistor. So who got 3 out of, all the 3 questions right? That was good work. Very good. Keep it up.
Yes.
And if you failed it, you have seen the mistake you did. Now, there's this question you did in your end of term. Have you revised it? Do we need to go through it?
Go through it kindly.
Go through it.
The circuit diagram that you had in your exam. So let me just draw it here. Then we solve it. I hope you have copied all these solutions. I hope you have all copied the solutions because I want to clean it. I want to clean that part. So let me draw it. You see, now the only trick that it had is that it had what? It had also an internal resistance of the cell, which is adding up, and again there were several resistors in interesting connections. So let's draw it here. So it was having this. We have this resistor. This is 1 ohm. Then we also have here 7.1 ohm. This is 4.5 ohms. Then at the middle, we have 3.2. This one comes, and we have an internal resistance R of the cell that is adjacent here. Then we also have 5.8. Then this comes and completes. So that was the circuit that was there. The top one is 7.1.
Relax.
So let me see that. Let me stop the share a little bit. Now we can take the roll call. We can take the roll call so that before we proceed, take the roll call kindly. So we can do it quickly so that we get back to our question. Yeah. So those who are not taking the roll call, kindly do it quickly so that we don't waste time. We are still waiting for around 40 of you have not participated in it. People, 37 people keeping us waiting. Okay, fine. Then we can proceed so that we don't.
Excuse me, Story.
Yes.
When we say that two resistors are in series, and we say that the current passing through the two of them are the same, does it mean that the first resistor offers negligible resistance or even no resistance, such that the current passing through the first resistor is the same as the second?
Okay, the idea of current passing through them is based on, let me draw something here to explain that. Now, I want to consider these two scenarios. We are having this and also this. Then this other scenario, of course, you're having a junction here, like that. Then this, and then a simple circuit having a bulb and something there. Like that. So this scenario, the last one I've just drawn, will the bulb light? Will the bulb light?
No.
Who has a reason as to why? Why?
The switch is not closed.
The switch
The
is
switch is
open.
not closed. Very good. So the current is not in a continuous or a complete path. Because for us to talk of current to be flowing, okay, let me talk of what happens. Actually, the electrons are supposed to be flowing from throughout the negative all the way to the positive. So the current have to come like that. Then it has to pass through there, of course. There must be a complete path such that we complete the circuit for the current, the idea of current to come in. So there's nothing that is happening much here. We're just trying to get what is the current that is flowing in this circuit. So if it is 2 amps, we only talk of 2 amps when it is able to flow until it comes back like that. Is when we talk of a current being existing then in that case. Otherwise, if it is open, there's no current. So the question comes in, is it not possible that this bulb will take up the current? What will always differ will always be the potential drop. If you potential drop or maybe the voltage, if you are to have another bulb on the same path like that. So the current will be coming, but now the potential drop that will be there will be different. In this scenario, we are talking about a current coming in and it also needs to come out. It will come, then reach at this point, there is a junction. So there's a path there, there's a path there. So it has to be split up. Some have to get through this path, others have to get through this path, then rejoins, but finally, when it comes out, the same should come out. That's what we normally say, the catch of the law. That says that the current coming in must be the same as the current that is coming out through any junction. If you are to have a junction, the current that comes in should be the same current that will always come out. So this one should add up to the same as the one that is coming out. And at the end of it here, the one that are coming in, they need to add up to the one that is coming out so that we preserve the value that is here and also whatever that is there. So the same that is happening to the ones in series here. The current is coming and there's no any junction where some current has branched through and all that. So just following the same path and that's to complete until back to the negative terminal. So that's how the flow is taking place. The only thing that will differ in this case will now be the potential drop, because based on their resistance, if this is having a resistance of maybe lower, this is higher, the potential drop here will be low, or the potential drop here will be higher. The potential drop is more of the idea of the energy that the work that has to be done in pushing or making the currents or the charges pass through. That's where the idea comes in. When you introduce talk of the potential difference to be the work done in moving a unit charge, of course, through a conductor, through a certain distance. So the only difference that in this case, much work may need to be done, of course. And when much work has to be done, that's why the difference will now come in. Whether we need to do much work or less work needs to be done. So that will give different in potential difference. The charges are the same charges that needs to flow through. The charges are not changing.
Oh, thank you.
All right. So this our circuit was this way, as you can see it on there. So for you to solve these problems, especially if the circuit is not very clear, like the one that we have here, you're supposed to try and redraw it so that it is much easier to understand. You're able to see the ones that are in parallel, the ones which are in series. It is time for us to pray.
Yes.
Who is praying with us? Anyway, let me not bother you with my devotional life. Anyway, let's just get back. Somebody want to read for us the Bible and pray?
Yes.
Yes.
But we can do that tukimaliza. Wacha tumalize kwanza. Make substations.
Okay.
Yes, wacha tumalize.
Yes.
Tukimaliza tuombe ya kwamba Mungu atusaidie tuweze kukumbuka na kuyaelewa hayo ambayo tunasoma siku ya leo. Okay, let's proceed. So let's try to redraw. Now, how do you redraw this? Again, I told you, get back and see where the positive terminal is. The positive terminal is down here, like that. So that's the part that current will follow. So always try to assign the direction of current in this circuit. They'll be moving that way, of course, then it comes, get there, like that. Then you'll see at this point, there's a branch that needs to be, there's a branch that is there. So this will come, of course, will proceed. The one that passed through that path will proceed like that, comes in, then they come and rejoins and get back. So that is how it will look like. So you can redraw it so that it looks like that. You begin from you can decide and begin from this resistor R. That's resistor R. So if that is a resistor R, like that, then as that direction goes by this R, we are going to meet the 4.5 on our way. So we have 4.5 resistance on our way as we move, like that. After the 4.5, we meet the 1 ohm resistor. So we'll come and meet the 1 ohm resistor. 1 ohm resistor will be waiting us there. Then after the 1 ohm resistor, there's a junction. That is the one that goes to the 7.1 and also 3.2. So you create that junction here, like that. Then you attach upper Ju will be the one that goes at 7.1, while this other one down here will be the 3.2. Then from there, you still proceed with your path. From the 3.2, from the 7.1, it moves and gets the 5.8 on the way. So it will move like that, then you get the 5.8, like that. Then from the 5.8 and from the 3.2, they combine to go back to the source. So this one, just extend it this way, extend this one this way, and then complete like that. So that is the redrawn network. So if it is this way, it is very easy to see. You can easily interpret the ones in series, parallel, and you can easily add them up. So you can either leave it hanging like that, or if you like, you can bring this one back like this. This one, you can bring it back, then show that this is positive, this is negative, and the supply was 12 volts. 12 volts, like that. So this is the first thing you should always try to do somewhere. Otherwise, you'll easily mess up on that network. You just try to ensure that, and how to get it, follow it with the current from the positive terminal as it goes towards the negative terminal. Is that okay?
Yes.
Yes.
And now let's start. You start with the branch that looks more shaggy. And the one will be this side. This side is where it looks much more complex. So we start reducing them, the one that are in parallel. Before you get there, check these two. You combine these two. So combining those two will be 7.1 plus 5.8 will be
12.9.
12.9.
12.9. 12.9. So these two, which are in series, can be combined to give us 12.9. So if you like, you can redraw your structure. And I don't want to redraw it again, but you can redraw so that you see what will happen now. So you can have one resistor replacing these two here in that. Then now, again, like I said, being the ones in parallel, 12.9 and 3.2. The two are in parallel. So let's combine the two in parallel. So R total for them will be R1, R2 divided by R1 plus R2. So you can take that 12.9 times 3.2 divided by 12.9 plus 3.2. So that will give you, somebody can do them quickly so that we finish up.
2.56.
So 2.56 ohms. So if you are to redraw, let's try to redraw this structure. It will look like this. We'll have the R unknown there. Then the next one will be 4.5. Then the next one will be 1. Then the next one will be now the total that we have just obtained. Remember this one here, the whole of this one, we have reduced it to be 2.56. So 2.56, that's the reduced one. So from here, all of them are now in series connection. So to find the R effective or R total now for all of them, you now can add them. Now, did you have the internal resistance, the value of R?
Yes.
In the question? Yeah, it was given, by the way. It said that in the circuit diagram of figure 6 below, the total internal resistance R of beta is 0.4. Yeah, actually it has a value. It is 0.4. It is 0.4. So you simply added them up. 0.4 plus 4.5 plus 1, then plus 2.56. So if you add all that, that is 4.9, that is 5.9, that should be 8.46 ohms.
Yes, yes.
Yes, 8.46 ohms. So that is the total resistance. So if you fail to get this one, it was very hard for you to get any other question that was to follow. 8.46. And you have seen how we have decomposed it. You redraw, then now reduce it using the laws of how to reduce the resistors until you obtain something which is easier. So from there, Roman 2. Oh, before we have moved to Roman 2, any question? A question? Okay, if there is no question, then we can proceed to Roman 2. So Roman 2 asks you to find the current flowing in the circuit through R. So we just want the current through R or through the 0.4 ohm resistor. And let me raise more space here. So current through R, that is the 0.4 ohm resistor. So the first thing, remember we already have the total voltage, we have the total resistance in the circuit. What else do we have? We were also given that the supply voltage was 12 volts here. So we already have the total voltage, you have the total resistance. So the next thing we need to find also should be the total current in the circuit. That's the first thing. It will always be helpful for us. So the total current that is flowing there, I is supposed to be V over R total. And V is given as 12 divided by R total, which is 8.46. This will give us the total current in the whole circuit. And that current will be, so 12 divided by 8.46, 1.4? 418. Yes, that is the current that is total current that is flowing through. So let's see. This total current, let's go back to our decomposition. Is the total current that is flowing in the whole circuit. And remember, the whole circuit can be replaced by one resistor of 8.46. And before we reduce it to 8.46, all the resistors were in series. And for series, we normally know that the current needs to be the same. The same current passes through them. So that current of 1.418 will pass through the R 4.5 through 1 and through 2.56. So the current through the resistor R is simply this. This is the answer, 1.418 amps. That's the current passing through that internal resistance of the cell, that is R. Iko sawa? Is that okay?
Yes, it is.
Yes.
Then the next one, part 3, Roman 3, will be to get the current through. So current through the 3.2 ohm resistor. So let's check where that 3.2 ohm resistor is in our reduced system. So 3.2 is somewhere here. It is here. This is where it belongs. So if it is there, then we go back. It was whatever was there was reduced to two resistors, which were in parallel, and then again was reduced to this 2.56, like that. So we know two things. Number one, we know that from the resistor where it belongs, the total resistance there is 2.56. That's one thing we know. Number two, we also know that the current flowing through the 2.56 should also be the same current that you have found up there, is 1.418. So let's use those two to get the potential drop or the voltage across. So the voltage there would be IR, and that would be I, and I is the one we have found up there, 1.418 times the resistance that which was effective. This one here, the effective that in that case was 2.56 times 2.56. So this will give us a value of 3.61 times 2.56. So 3.63. So 3.63 volts. So that is the voltage drop. That is the voltage drop. And also 3.2, and they were in parallel. So if they are in parallel, then it means that they are under the same potential. So the same voltage drop which you have found there, that is passing through them, is the one that is through the 3.2 and also through the 12.9. So that voltage drop you have just found, the voltage is also the same voltage that is passing through the 3.2 ohm resistor, the one we want in the question. So you already have its voltage drop is that one. We know its resistance. So you can find the current as V over R. So the V is the voltage drop that is there, 3.63, divided by the resistance, which is 3.2. And that will give you
1.134.
3 amps. It is a current. Yes, like that. So that is the problem that you are required to solve. The problem that you are required to solve, which I saw most of us could not get it right. Most of you. And I know because of how the network was drawn and also the introduction of the internal resistance R of the cell therein. So just treat it like any other. Don't worry that internal resistance is an issue there. Just always, it will always be in series with other things. So you can always add it up together with the others. So any other question? Any other question?
No.
I hope this one won't be an issue again. Maybe this issue of networks is very important, very, very important for part 2. It will be there in any way part 2 you'll be doing. And even next year, in your case, you expect to find a question on these networks. So maybe just as a takeaway home, as we end, is I'll draw for you just as a circuit here, so that you can try. It will be a little bit complex, kidogo, but just for your practice, I can draw for you one. It is good you have one, right? You test yourself with, but ensure that first of all, the ones you have done, you try go through them. Also practice what you have learned. Take your textbook if you have it. I also try to go through the exams that solve there, the questions that are there, applying what you have learned. Then it's always about practicing. So the more you practice, the better you become at them. So once you are sure that you have understood how to decompose, to redraw the circuits, and also how to get the current in each of them, you will finally come and attempt the one I'm drawing here. So I'll draw it here. You can draw it with me, or once I've drawn it, you can just take a screenshot. It will still go a long way in helping you revise. So here it is. So I have there. This is 9. They're all in amps. I don't want to write the word amps in them. This one is 34. Then we have one here. That is 10. $19. Then there's one connecting the two here. That is 18. 18. It is 18. Let me write it from the outside. 18. Then this proceeds. 5 ohms. Then this one comes. Another one upper katikati. This is 21 ohms. Then the whole thing is connected from the left hand side. So this A and this B. So the current comes in at that point A and then comes out at point B. So you'll find you can have that circuit, screenshot it, or maybe write it somewhere. You'll find for me the total resistance in that circuit, and also the voltage drop across each resistor, all of them. Find the voltage drop across them, given that the current in the circuit is 5.6 amps. So the total current that is in that circuit is 5.6 amps. So use those information. So the one that is coming here is 5.6 amps. So use that information to get, for me, the total resistance and then the voltage drop across each of the resistors. And that will be a good exercise for you to practice. In case there's any other question before we call it a day. No question?
No.
All right. So then I wish you all the best. I wish you all the best. Keep practicing, keep revising, and no, we shall improve.
Thank you.
Yes.
Thank you.
Thank you.
Thank you.
Karibu. So someone was to pray with us before we end. What was the one to pray?
Tamula.
So who is praying? No one want to pray.
Let us pray.
Okay, Maxwell Jorams, please pray with us.
We are praying. Almighty and ever-living Master, we want to say thank you for the gift of life, O Lord. Thank you for the wonderful lesson that we've just had. And oh Lord, we pray that whatever we have been taught, may it stick into our brains. May it be helpful whenever we're doing our examinations, oh Lord. Father, as we prepare to go back to school, be with each and every one of us. May you give us journey mercies. Father, be with our teachers, protect them until we meet again. In Jesus' name, I do pray and believe. Amen.
Amen. Amen. Thank you so much, Maxwell Jorans. May God bless you and all the best. We can end it now.
Thank you.